Okay, so we're going to start. Okay, good morning, everyone. Welcome to this special session of the research seminars. Today we are welcoming Professor Serge Haroche. He began his research career at the Centre National de la Recherche Scientifique and later became a professor at Pierre and Marie Curie University. Over the years, he also had teaching and research positions at leading institutions such as École Polytechnique, Massachusetts Institute of Technology, Harvard University, and Yale University. He later became head of the physics department at the École Normale Supérieure and since 2001 has been a professor at the Collège de France, where he holds the chair of quantum physics. In 2012, Haroche was awarded the Nobel Prize in Physics together with David Wineland for groundbreaking experimental methods that allowed the measurement and manipulation of individual quantum systems. Their work made it possible to observe quantum particles such as photons without destroying them, something previously thought impossible. This achievement opened a new era in quantum experimentation and laid important foundations for future technologies like quantum computing, which could revolutionize information processing in the same way classical computers transformed 20th century. So I let you. For you.
Okay. Thank you very much for this nice introduction. I apologize first for speaking sitting because I have a bad knee and it's painful for me to stand up for a long time. As has been said, I belong to two very old French institutions. One is Collège de France, which was founded in the 16th century by the King Francis I, and in which you have professors who teach in all kinds of fields. My field, atomic physics, but also there is astronomy and cosmology and high energy physics groups there. And on top of that, chemistry, biology, and social and science and humanities. And the other institution is the École Normale Supérieure, which was founded during the French Revolution, and which is also a very well-established institution where students are trained to become professors or researchers, for example, at CNRS. I am not, of course, a specialist of astronomy or astrophysics, but as we will see, there is now a common interest in science between different subfields of physics, and quantum physics has strong connection with cosmology and with astronomy, and I will try to give you a few examples of that, which in fact come back to a very old past. As you know, last year and this year, we are celebrating the 100th anniversary of quantum physics. It is in January 1926 that Schrödinger had established the famous equation, which was the real start of modern quantum physics. And so I have been giving many talks on that topic connected to lasers. What I wanted to tell you in this talk today is that the laser has been always very strongly connected to quantum physics. First, because it is an offspring of quantum physics. The laser would not have been possible without the knowledge of the microscopic world we got from quantum physics. And then, as soon as the laser was created, it was used as a very important tool to acquire more information about the quantum world. We all know, of course, about all the application of the lasers to technology, but what I want to focus on here is what the laser has brought to fundamental knowledge, and especially fundamental knowledge in quantum physics. So my talk will have two parts. In the first part, I will recall the history of the laser, how it was founded after many, many years of research in quantum science. And then as soon as the laser came into play, it has been used as a tool to get deeper and deeper into quantum science. And so I will talk also how it has made possible to make breakthrough in quantum physics. And I will say a few words about the promises it holds for further discoveries in basic science. And I also want to use this talk to show the strong connection, the symbiosis between basic research and technology. Basic research leads to technology. And on the other hand, as soon as you get new tools, you can get deeper and deeper into acquiring new knowledge. And so basic science is very important. So I will be starting by the history of this field. And in fact, it started well before this year of 1925-26. It started with what we call the old quantum theory. And I would just very briefly recall the main stages in 1900 and 1905, the work of Max Planck and Einstein, who discovered that light, which was supposed to be just a wave before, was also made of discrete quanta, discrete particles, which were later called photons. And this was important to explain the strange features of the black body radiation or the thermal radiation, which could not be explained by classical physics, and also the photoelectric effect. So in fact, this was the beginning of the quantum world because it opened a kind of Pandora box where we had to understand how wave and particle aspects of the world could be reconciled. And this is, of course, also the time when Planck introduced the famous Planck constant, which was going to play such an important role in quantum physics. Then a few years later, Bohr used for the first time this idea of quantization to explain the spectrum of atoms, especially the spectrum of hydrogen. He found that the orbits of the hydrogen electron had to be quantized in terms of energy, and that the jumps between the orbits were being explained by the emission and absorption of photons of quantum of light. And it was the first paper in which Planck's constant entered into the explanation of the properties of matter. A few years later, Einstein tried to recover the laws of thermal radiation by making the balance between absorption and emission of light by atoms. And he found out that in order to do that, he needed to introduce a new process called stimulated emission, by which an excited atom, which was receiving light, was amplifying this light, emitting identical photons to the photons which were impinging on it. This effect of stimulated emission would be exploited, would be essential to build the laser half a century later. But Einstein already had this idea that the photons were undistinguishable because the photons which were added when an atom was emitting photons stimulated by other photons, they were identical to the impinging photons. And this idea was strengthened in Einstein's mind when he received a paper by Bose in 1923. Bose was a young Indian physicist who rediscovered the laws of thermal radiation, Planck's law, by assuming that the photons were absolutely undistinguishable particles. And he made a count of states which was quite different from Boltzmann's one, explaining that configuration in which two particles were exchanged between two states were just a single configuration. And Einstein immediately understood that if you applied these new statistics to atoms, which we later called bosons, you would find that at a very low temperature, all the bosons would fall into the same quantum state, making a new kind of state of which does not exist in nature, which was called Bose-Einstein condensate later. And this discovery was made by Einstein on purely theoretical grounds in 1923, and it took 75 years before, due to laser, it was possible to realize this kind of condensates. So this brings us at the end of the old theory of quanta before Schrödinger's equation, and about that time in 1924, Einstein received the thesis of De Broglie in Paris, and De Broglie had made one step further. He had assumed that this duality between wave and particle, which Einstein and Planck had applied to light, should also be applied to matter. If matter was classically considered as being made of discrete particles, it should also be associated with wave. And so this duality between wave and particle was extended to matter. And Einstein immediately reconciled this with his idea about Bose-Einstein condensation, the connection between photons and bosons. And so he replied to Langevin, who was a professor at Collège de France, who had a connection, who was a thesis advisor of De Broglie. He wrote to him, "Your student has started to lift the veil which is hiding the mysteries of the quantum world." And in fact, Einstein was right, because a few months later, Schrödinger, trying to find the equation which describes the propagation of the Broglie wave, established Schrödinger's equation. And so this is a connection between these studies about light, matter, and the quantum world, which were very important for the discovery of the laser. All this is theoretical, but I have to quote another breakthrough, this time experimental, which played also a very important role for the invention of the laser, which is the experiment that Stern and Gerlach did in Hamburg in 1922. In fact, what they were trying to do is to measure the magnetic moment of atoms. It was clear since the work of Ampere in the 19th century that the magnetism of atoms was due to electric currents in the atoms and molecules. But in order to measure these magnetic moments, Stern invented this experimental setup that you see here. Silver atoms were escaping in a vacuum from a furnace. Silver was heated. It made a beam of atoms propagating in the gap of a very powerful electromagnet, which produced a gradient magnetic field. The idea was that this magnet would deflect the magnetic moments up or down, and by measuring the deflection, one would measure the magnetic moment. But what they expected to see is a continuous trace, because classically the projection of the magnetic moment along the direction of the gradient was continuous. And to their surprise, what they observed, in fact, there are two spots corresponding to only two possible orientations of the magnetic moment, up and down, which we call now spin up and down. So this setup, which separates the magnetic moment, shows the spatial quantization. So it's not only the energy levels which are quantized, but also the spatial direction and amplitude of the magnetic moment, which is quantized. So this experiment is the first one which shows a two-level system in quantum physics. So this is the ancestor of, for example, what we call now qubits, quantum bits, which store information into 0 and 1. You see here the trace that they observed. It's just a glass plate situated downstream, and you have kind of two lips because the gradients were decreasing on the side, so the separation is well visible at the center. And in fact, they saw this trace because when the silver was deposited on the glass, it made silver-sulfur molecule, because the story says that they were smoking in the lab, which is completely forbidden now. But without the smoke, they would not have had the sulfur, and the silver would not have been visible. So it was a very crude way of detecting things, and it detects much better now. But they understood that this trace was very important, and so they put their experimental result on a postcard, and they sent the postcard to Niels Bohr in Copenhagen, because Niels Bohr had been the first one when he made the theory of the hydrogen atom to say that the angular momentum of the electron was quantized. In fact, he was talking about orbital quantization, and here it's the quantization of the spin. But nevertheless, they recognized it was a very important result, and they sent a postcard saying, "We congratulate you for the confirmation of your theory," which was not really the confirmation of the theory, because Bohr did not believe into the spin quantization, but this is another story. And what I want to stress is that this simple split trace on the glass plate announces the 20th century quantum revolution in technology and the qubit in the 21st century. So this was really the pre-modern quantum era, ending up in 1925. But now I will talk about what happens after that, and I want to mention the very important work of Isidore Rabi. Back in the 1930s, Rabi was a postdoc of Stern, and when he came back to the United States, he started his own work at Columbia University, where he decided to measure not the electronic angular momentum, but the nuclear magnetism, which is 1,000 times smaller, so he needed a better setup. And what he designed is this improved Stern-Gerlach setup, Now you see that you have two gradients in zone A and B. So the magnetic field are pushed in magnetic moments are pushed in one direction in zone A, in the opposite direction in zone B, which makes them go on the kind of S-shaped trajectory, focusing on a hot wire. On this hot wire, the atoms or molecule lost an electron and gave rise to an electric current proportional to the flux of particles arriving at the hot wire. Now, the improvement the most important improvement was zone C. In zone C, we applied a radio frequency wave, which emitted photons, which are matching the energy, difference between the spin up and spin down. And so the separation between these two zones, between the two levels, was matched by photons which had the right frequency. And so what happened if you applied the right frequency in zone C? The spin was flipped, and so it missed the second. It was deflected in the wrong direction in the second zone, and it missed the detector. And so what they observed when they scanned the frequency of the radio frequency field, a dip into the signal to the detector, and this is the first magnetic resonance observation in 1939. And so by finding out at which frequency for a given magnetic field this resonance occurred, they were able to measure the magnetic moment of hydrogen, deuterium, and a lot of other atoms and molecules. And so this signal, this was Rabi magnetic resonance. It announced the nuclear magnetic resonance, the magnetic resonance imaging in medicine, the atomic clocks, the GPS, optical pumping, the maser and the laser. All this is contained virtually into this first result. And in fact, Rabi had the premonition that things like that will happen. In 1939, he gave a conference in which, some journalists attended, and you see here the headline of a paper, the New York Post, in December 1939, which said, "We are all radio stations, Columbia scientists report," because Rabi had said that in our body we have atoms and molecules, which, like the atoms and molecules of my atomic beams, emit and absorb radio frequencies at well-defined frequencies. So they are like radio stations, and if we're able to catch up these radio waves, we would have a lot of information, maybe about the inside of our bodies. So it was already the germ of medical magnetic resonance imaging in medicine, for instance. But of course, before you get to that, you have to make a lot of progress. We cannot investigate the molecules inside our bodies by putting them in an atomic beam, which is very destructive. So the next step was made by Bloch and Purcell in 1946, which developed nuclear magnetic resonance in bulk materials, solids and liquids. In this time, the resonance is detected by detecting the absorption of energy or the emission of radio waves when you hit this molecule with the right radio wave frequencies. And what I want to stress is that this was made possible because of the progress of radio wave technology during the war, when the radars were developed in England and the United States. This is another example of the connection between basic science and technology. So, and of course, after many, many years, when you introduce very high magnetic fields produced by in superconducting coils, and when you add up all the technology of computers which are able to transform these signals into images, you get MRI about 30 years later, starting in 1970s. Another just consequence of this work on magnetic resonance is the work on atomic clocks. Norman Ramsey was a student of Rabi, and he was instrumental in the development of the cesium atomic clock. Cesium atoms have a two-level structure, depending upon whether the electron and the nuclear spin are aligned or anti-aligned, and the separation falls in the gigahertz range, 9.2 gigahertz, And so if you induce a resonance between this state, you have a microwave which can be locked to this frequency, which is a very stable, according to quantum laws, the same for all atoms of cesium in the universe. So this is the basis of the atomic microwave clock. And Ramsey improved the setup by having the atoms go through two separate radio frequency fields. It's called the separated oscillatory field method. And when you scan this magnetic field, instead of having a Lorentzian curve, you get fringes. It's a quantum interference effect. It's because the spin can flip in the first zone or in the second zone, and the interference between the probability amplitudes leads to this kind of fringy signal, which gives a much narrower structure. And if you lock your microwave to the top of the central fringe, you get a very stable microwave, which counts the time with a precision which is fantastic. The clock which is locked on this setup does not shift by more than 1 second in millions of years. And these clocks are now sent into a swarm of satellites orbiting the Earth, and the signals, the microwave signals they send, they are synchronized with each other, and the signals they send to each other allow us to locate ourselves on the surface of the Earth with a precision of about 1 meter. And so this is one consequence of this two-level system. Another big improvement, and all this was in fact started before the laser. It was research in the 1950s. Another research of the research in the 1950s was the optical pumping. By optical pumping, you manipulate the magnets, atomic magnets, not by gradients of field like in the Stern-Gerlach experiment, but you manipulate them by sending on them polarized light, which carries angular momentum. And this is the basis of optical pumping. You see Kessler is holding a cell in which you have a lot of atoms, for example, mercury or rubidium atoms, and these atoms can be oriented by light, by shining on them circularly polarized light. So there's a possibility to orient magnetic moments by optical means. And if you orient the atom into the upper level, you get a negative temperature. And if you diminish the number of atoms in the lower level, you decrease the temperature according to thermodynamics. And Kessler was working with Brossel, said that this was a way that it might be a way to cool matter by having it interacting with light. So it was also a premonition of what became possible with lasers. A student of Kessler and Brossel was Claude Cohen-Tanucci, who in 1960 discovered what we call the light shift effect. If you shine light on an atom which is not resonant, the photons cannot be absorbed because there is no conservation of energy, but non-resonant light slightly shifts the energy level of the atom. And this shift is proportional to the light intensity. So if you have a change of the light intensity, spatial change, that is a light gradient, it will lead to an energy gradient. And an energy gradient is a force. So there is a way to exert forces on atoms by shining focused light on them. And this is something which will be exploited later with lasers in the way I will explain later. Also, it also says that you can measure the number of photons in principle in a light beam by looking at this force which deflects the atom, because this force is proportional to the number of photons. And this will be also the origin of the quantum non-abolition way of counting photons, which plays now a very important role in quantum information science. But at the time, before the lasers, these effects were tiny. The light shifts that Claude Cohen-Tanucci observed were of the order of 1 Hertz only, and they will be observed by the technique of optical pumping. Now the shifts are hundreds of gigahertz, 10 orders of magnitude larger, and they give rise to forces, to macroscopic forces acting on single atoms. So this was 1960, and this is the year where the laser was invented.
¿no?
So
vale.
we'll go back to this now.
Bueno,
And,
¿a qué hora te levantaste?
This is an interference, but not a quantum one. So, okay. So for the laser, I have to come back to Columbia. You see here Towns and Incident Gordon in their lab at Columbia University in 1954, and they stand in front of a molecular beam, which is the same kind of beam that Stern was using. This beam was a beam of ammonia molecule, and the ammonia molecule is a two-level system. You see here the 3 hydrogen atom and a nitrogen atom, which makes a kind of tetrahedron. And the nitrogen can stand on one side or on the other side, and it goes across the plane of hydrogen by tunnel effect. And this gives rise to emission of microwave at a frequency of 0.23 gigahertz. So it's a two-level system. And if you put the eigenstate are the symmetric and antisymmetric superposition of these two configurations, if you are able by Stern-Gerlach method to put the atom in the upper energy state, it would amplify the microwave. And this gave rise to the first coherent sources of microwave called a maser, by an acronym for microwave amplification by stimulated emission of radiation. And so this was the ancestor of the laser. After that, during a few years, many scientists tried to extend this to the optical domain. This was achieved by Maiman in 1960, and it was at the beginning called the optical maser, which is a kind of strange vocabulary because it put optics and microwave together, and later on becomes a laser, light amplification by stimulated emission of radiation. So and I will not describe the technology of lasers, but I just want to summarize here all the properties of the laser which made a lot of things possible which are not possible with classical light. It's intense, it's directive, it's monochromatic, and it's coherent. So with the intensity, what you can do with the intensity is to heat matter at huge temperature. By focusing a very powerful laser on a solid material, you can achieve fusion and evaporation of matter, and you can even reach temperature high enough to induce fusion reaction inside nuclei. This is a very intense laser which are used for military and for civil application in various countries. But paradoxically, you can also use this power to cool matter. If you send a laser beam, counter-propagating laser beams on matter, you can make the latter absorb the momentum of the atoms and cool them down to extremely low temperatures. And these temperatures can be so low that they reach the point where Bose-Einstein condensation occurs. And when you get Fermi-degenerate gases for fermions, this temperature is the order of pico and nanokelvin, so 10 orders of magnitude. At this temperature, the atoms are propagating at velocities of the order of millimeter per second and not hundreds of kilometers per second. And the de Broglie wavelengths extend to large distances, micrometers or larger. So this is one application. Now, the stability, the monochromaticity and stability leads to other kind of application. You can have ultra-stable light beams which oscillate without skipping a beat over millions of kilometers. You have now a technology which allows you to send a laser beam to the moon and back, and to make the returning beam interfere, make interferometer of this kind of size, which is absolutely unbelievable. And also, if you make very stable monochromatic laser beams coherent in phase, they will interfere with each other and make rise to bursts of radiation, very short bursts of light, periodic bursts of light, each pulse of light being very, very narrow in time, and you get down to attosecond laser pulses. 1 attosecond is 1 billionth of 1 billionth of a second. And you can make a very study of stroboscopic study of matter with a very, very high time precision. So this is kind of thing I will briefly comment later, but what I want to say is that fundamental research in physics, but also in chemistry and biology became possible with this extraordinary source of light. And again, I am only talking about basic science, not about all the practical applications that we know about lasers. Just to give you an idea on this on this slide, I will just give some orders of magnitude. I want to stress the fact that over the last 65 years, the laser has made tremendous progresses which have led to quantitative and qualitative evolution in basic research, and in more than 10 orders of magnitude of improvement have been made in many directions. And 10 order of magnitude means a factor of 10 every 5 years. So it means that for graduate students, it has a lot of consequences. It means that when a graduate student starts his thesis, the time it finishes, the technology he has used has improved by 1 order of magnitude. So it means that you have really to stay on the top of the technological development all the time. So let me compare what we could achieve in 1960 and what we can do now. Now, the temperature and kinetic energy of atoms. In 1960, the atoms were usually studied at room temperature. And if you want to have cold atoms, you could put them in a cryostat. You can try to cool them, but it was difficult to go below 1 Kelvin. Now, with laser cooling, you can go to nano and even less than nano kelvins. So you get 9 or 10 out of magnitude easily. The precision. In 1960, the best frequency, the best spectroscopic measurement you could make were in the range of 10⁻⁸. For example, Rydberg constant was measured with 8 significant digits. Now you can measure the atomic frequencies with a precision with 19 or 20 digits. And this is also the improvement made by clocks, because the clocks are based on the spectroscopy of atoms. In 1960, the best precision of clock was in 1 part in 10 to the 8, which was already a tremendous improvement over the clocks which were used. The pendulum clock, for example, has a precision of 1 part in 10 to the 4. So there have been, between the time of Roy Hens in the 17th century and 1960, the progress was 4 orders of magnitude. Since 1960, 10 more orders of magnitude have been added with optical clocks. The sensitivity of measurements in the kind of optical cells that I showed you, even if you had a tenuous gas of atoms or molecules, you had billions of atoms in the cell. Now we can interrogate a single atom, or you can store a single photon in a cavity and study how the single atom interacts with single photon. The speed and time resolution, the flash of light you could realize in the 60s were micro, maybe nanoseconds. Now, as I told you, you can reach the attosecond level. The last one I want to mention is the sensitivity to length variation. When you have a cavity made of mirrors, how precisely can you measure the change in the distance between the mirrors? The interferometer, which defined the meter in 1960, it was a Michelson interferometer, which was observing a line in the molecule, a krypton atom. And this had a precision of 1 part in 10 to the 8, which is a fraction of micron over meter. And this was the definition of the meter. Now, as you know, in the LIGO and Virgo interferometer, you get a sensitivity to mirror displacement of the order of 10⁻21 to 10⁻22, which is 1 billionth of the size of an atom over a distance of 4 kilometers. And so it's an improvement which is related to the stability, of course, stability of lasers. Not only you have also stability of the mirror vibration, so it's a breakthrough, it's a kind of tour de force, not only in optics, but also in mechanics. So let me just go very quickly through these different improvements. Laser cooling. You see here at the center, you have a cloud of very cold sodium atoms, which are the intersection of 6 laser beams. These are counter-propagating laser beams in all directions. The main effect is, the cooling effect is a Doppler effect. The fact that if the atoms move in one, the laser light is slightly detuned, which means that if the atom moves against the laser beam, they will put more in resonance, and so they will absorb more photons coming from one direction from the other. And if you detune the laser on the red side of the transition with all these beams, it means that in whichever direction the atom goes, it will receive more momentum to decrease its velocities and momentum to increase it. And so this is called a quantum molas. Because it's like the force is like the force you get, the viscous force you get in a molasses when if a small ball or a small piece of matter is falling into the molasses. But here the molasses is produced by photons and not by matter. And so at the intersection of the laser beam, you get a very cold ensemble, about 1 million atoms. And by measuring the temperature of these atoms, to measure the temperature, what you do is you switch off the lasers, and so the cloud of atoms expands, and by measuring the speed at which it expands, you can deduce the velocity and then the temperature of the atoms. And what people found, what the experimentalists found 40 years ago, is that in fact the temperature was even much cooler than my model could explain. So there is an effect which very rarely in physics goes in the direction you want. Usually when you have an effect you don't understand, it has the result of being bad for what you wanted to see. But here, at the beginning, nobody understood why you could get a temperature lower than what was predicted by this model of exchange of momentum. And the explanation was given by Claude Cohen-Tanucci and Jean Dalibard. It's called the Sisyphus cooling effect. And it relies on the fact that in the ground state of these atoms, it was a two-level system, like the cesium atom, and you could have optical pumping. The light process was bringing the atoms from one level to the other one. And this effect combined with the light shifts. You see the interfering laser beam make energy landscape, which gives maxima and minima of energy, which means that when the atom moves, they have to climb or to go down an energy hill, which gives rise to a force. And so what is combined here is that the atoms are going up an energy hill and for one level, and when they get to the top by optical pumping, they are brought to the bottom of the energy level for the other state. So I don't have time to enter into the detail, but the combination of this climbing hill effect and this resetting to the lower state as you are up makes the atom always climb energies. And it's like the Sisyphus character of the Greek mythology who had to work against gravitation all the time. Here you have to work against these light forces until you get at a very, very low temperature. At that point, you can even go lower by doing what is called evaporative cooling, which is just to make the hottest atom escape from this trap. And it is in this way that Bose-Einstein condensation was discovered in 1995. So, and this was the work of Wyman, Corner, and Ketterle. So you can now hold atoms in this Bose-Einstein state, coherent state of matter. And if you let the atom escape from this trap, you get a beam, a collimated beam of atoms, which is called an atom laser, in which the photons are replaced by atoms. And so you have the coherence of the laser beam, which is translated into the coherence of a matter beam. And this has given rise to a lot of research during the last 25 or 30 years. I have no time to enter into that. What about clocks? The last clock I talked to you about was a microwave cesium clock, which has a stability, a precision of 1 part in 10 to the 14, which is 1 second over millions of years. And this clock was locked on a microwave transition. Now we can lock clocks on an optical transition, strontium or ytterbium atom, which is 5 orders of magnitude bigger than the microwave frequency. And so you gain this 4 to 5 orders of magnitude in the precision of the clock. The uncertainty now is 1 part in 10 to the 19, which is 1/10 or 1/20 of the age of the universe, which means that in theory, if you had synchronized two clocks 14 billion years ago, they won't differ from each other by more than 1/20 of a second. And it means also that potentially you can have now a GPS which will be 5 orders of magnitude more precise than the present GPS. That is, instead of meter, it will be micrometers precision. Of course, you have to make a lot of correction due to the fluctuation of the atmosphere, and we cannot win this precision, but this is potentially what you have here. So 100,000 time improvement. And this means that the clock is now sensitive to general relativity space-time curvature over 1 millimeter altitude difference. And experiments have been done. If you compare the rate of the clock with the difference of altitude of 1 millimeter, you measure it. So in fact, and of course, the sample on which the clock is locked is more than 1 millimeter. It means that the clock doesn't have the same time at the top and at the bottom of the clock. So you have to make a lot of corrections, and it opened the way to a lot of very interesting tests of general relativity. Of course, special relativity was checked already with a high precision with ordinary atomic clocks, but here with these optical clocks, you can make very precise tests of general relativity at the level of millimeter or sub-millimeter. And one day you will reach a precision such that you will be able to measure the rate at which time changes on an electronic orbit of a single atom. And then it makes it comes to the question how to describe atomic physics at the level when relativity comes into play, general relativity comes into play. And it is, of course, a connection between quantum physics and general relativity, which is an open topic, but you see that this kind of experiments one day might give some answer. Usually, the common wisdom up to recently was that an answer to this question could come only from accelerator physics or cosmology, but maybe you will have an answer from the precision of atomic physics if you still improve things here. I want to say that this clock involves 4 different laser systems working together. You need first lasers to cool the strontium atoms in the way I described before. Once they are cold, you have to hold them in a lattice, because if they move, the Doppler effect will wash out the precision. And the lattice is made of interfering beams of light. And so these are the trapping the beams which trap the atom at a very well-defined point in a lattice. They have to be held 1 atom at a time in each point, and at a distance which is large enough so that the interaction between the atoms can be evaluated and controlled and corrected. The third laser is the laser which excites the strontium transition on which the clock will be locked. It has to be an ultra-stable laser which has a frequency stabilized at the millihertz level, and the frequency is 10 to the 14 hertz. So the millihertz level gives you 10^-17 or 10^18 stability in frequency immediately. But this is not enough because you cannot count optical frequencies. To count the frequency, you have to divide them by a huge number to bring the frequency down to the microwave that you can count with electronic devices. And this is achieved by a 4th level system, which is called a frequency comb laser. It's a laser which has 100,000 modes locked with equally spaced gaps between successive frequencies. And the frequency difference between 2 laser modes is the exact divider of the optical frequency. So what you do is that you lock 1/2 of this frequency comb to the atomic line, and you measure the gap between 2 successive combs, you get a divider, a microwave frequency on which the stability of the laser has been transferred, and then you lock this microwave to a microwave clock and you get the optical stability reproduced on the microwave. So it's really tour de force of all kinds of technology. And I want to stress that the frequency comb technique is now being used in astronomy, for instance, to measure, to detect exoplanets and to measure the periods of exoplanets. So there is a very strong connection with laser physics and astronomy. Just very quickly, I just here talk about another application, which is the application to quantum information science. Now, on this slide, you see that you can trap atoms. Here, these are ions, electrically charged atoms, which are trapped in a linear ion trap, and they repel each other. So, in fact, the combination of the attraction to the trap and the repulsion makes a string of regularly spaced atoms. And you can interrogate each atom by focusing a laser beam on it. And you see each of these bright spots at the top. At the bottom is one single calcium atom. And here you have 54 of these atoms. And you can manipulate these atoms individually and put them in a level which is bright. And you can see in a level which does not scatter the light. And you have a qubit. You have a system which has two states. You can distinguish them. You can make any pair of atoms in this string of atoms talk to each other, and you can build what is called quantum gates by having the state of one atom controlling the state of the other. And the dream is that one day, doing that not with hundreds, but with millions of atoms, you could get the operation of what would be called a quantum computer. But I want to stress that we are very far from that. And this experiment only demonstrate elementary steps of quantum computing, but again, it uses the property of laser light to optically pump now isolated atoms and to manipulate and detect them individually. In our group in Paris, we did the opposite. Instead of using light to control single atoms, we used atoms to control single photons. And we use special atoms called Rydberg atoms, atoms in which you promote one electron to a very large orbit. These atoms are very sensitive to microwave transition between nearby Rydberg state. And so we build a system which looks like an atomic clock. In the center, you have the cavity C, which now contains 0 or 1 or 2, or a very small number of photons. And the Rydberg atoms are crossing the cavity along an atomic beam. And you have the Ramsey interferometer, which means that you prepare a superposition of state in R1, you let it evolve when they cross the cavity, and you catch it up with a second pulse in R2. And the cavity field is slightly off-resonant, which means that the photon cannot be absorbed or emitted, but what the photon does is that it shifts the energy level of the microwave transition, and downstream you detect Ramsey fringes. By scanning the frequency of the field in R1 and R2, you get the probability of having the atom going from one state to the other, going up and down. And now, if you set up your system to be at the top of a Ramsey fringe with 0 photon, we are at the bottom of the fringe with 1 photon. And so the state, the exit state of the atom tells you whether you have 0 or 1 photon in the cavity. But the photon is not destroyed because it's a non-resonant process. The photon is just used to shift the transition in and out of resonance. And you see the kind of signal we get. For a long time, you have 0 photon in the cavity, then 1 photon pops in, stays for a long time, and goes out. And what does make the photon pop in and out? Just the thermal radiation law. We are not at 0 Kelvin, we are at 0.4 Kelvin. And so from time to time, 1 photon is emitted by the cavity walls, stays for a long time, and disappears. And you see that hundreds, thousands of photons see the same number of photons, which means that the photon is not absorbed by the measuring process. It's called a quantum non-devolution measurement. And you can use now this information about the photon number to do information processing, transfer the information from the photon to the atom, and so on. And this is called cavity QED. And this is a kind of experiment that we did with my group in Paris, and which was rewarded by the Nobel Prize in 2012. So it shows that you can use this basic interaction between photons and light to process information, to store information in the cavity or in the atom. And a lot of groups are now using that technique, either with Rydberg atoms or with artificial atoms, superconducting qubits, which are coupled by the same kind of interactions that the one I described here. The last point I would like to talk to you about here is another use of Rydberg atoms. Up to now, I have told you that Rydberg atoms are very sensitive to microwaves, but they're also very sensitive to themselves. If you have two Rydberg atoms close by, they interact by van der Waals forces, and this interaction can extend to several tens of micrometers because the dipoles of this atom is huge. So I show you here a very simple experiment. You focus a light on 2 points which are separated by a few microns. And at each spot, you trap a ground state atom, for example, a rubidium atom in the ground state. So you get two atoms which are closely spaced and tightly held so they cannot move. And then you try to excite them into a Rydberg state. So you can excite the first atom with laser beams to a very large state. But once you have excited one atom, the same light beam will be unable to excite the other one. Why? Because of the interaction. The van der Waals force will shift the other atom out of resonance. So you can only excite one atom. So you can tell yourself, oh, maybe it's because I try to focus. What happens if I now try to excite the two atoms together? But again, it will be the same thing. If you try to do that, you will be able to bring one excitation into the system, but the second one will be blocked because the same frequency cannot reach the second level. But what will happen in this case is that the excitation will be equally shared between the two atoms because you cannot know whether it will be the first atom or the second one which will be excited. And in fact, what will happen is that you will have an entangled state. You will have a single excitation symmetrically shared between the two atoms. This is called entanglement. And once you have entanglement, you can build quantum gates. You can make a system in which the state of the first atom will control the state of the other one. And so this phenomenon called dipole blockade is now used in a huge, hundreds of experiments around the world to try to build a quantum machine to do quantum simulation, things like that. You see here, for example, an example of atoms regularly spaced. And you have a bright atom means that the atom is in the ground state because it can fluoresce when it is in the ground state. When it is in a Rydberg state, you have a dark spot because you cannot see it. But this is an anti-ferromagnetic situation. If you assume that the ground state atom is similar to a spin down, the Rydberg atom will spin up, and here you have a configuration of anti-ferromagnetism where spin down and spin up are controlled in this way. So this is a kind of system in which you make quantum simulation of anti-ferromagnetic materials, and you can use this kind of experiment to do simulation of processes which happen in real matter, but at a quite different scale. In real matter, the atoms are separated by angstroms. Here, the atoms are separated by tens of micrometers, and you can address each atom individually. So you can study a lot of quantum phases, which will be very difficult or impossible to study in real materials. And it's also the system on which research on quantum computers are being made. The last point I would like to address, now I am looking a little bit into the future. The precision of this laser spectroscopy experiment allows us now to ask a very basic question. For example, is the electron exactly spherical? According to the standard model of quantum physics, the electron is just a point charge of electron, of electric charge, which is completely spherical, by which I mean has no electric dipole moment. There is no dissymmetry between the distribution of positive and negative charges inside the electron. And this is known, according to the standard model, if you had an electric dipole moment, it would have to be smaller than 10⁻36 electron centimeter. This is because an electric dipole moment would be the violation of time reversal symmetry. And according to the standard model, such a violation could occur at this level. Now you have, outside the standard model, you have a hypothesis saying that you might have supersymmetric particles, which would give rise to a larger violation of this time reversal symmetry, and which predict an electric dipole moment, which would be between 10⁻31 and 10⁻32 electron centimeter. This is exceedingly small, and I will give you some intuition of how small it is. But how would you do this kind of experiment? The idea is to have an electron submitted at the same time to a big magnetic field, which will make the spin process, the electron spin recess at the Larmor frequency. It's a very well-known effect. And if you add an electric field, you will have also a precession by the electric dipole moment around the electric field. So upon whether this electric field is parallel or anti-parallel to the magnetic field, you would have a small difference. But this difference would be exceedingly small, and it's impossible to apply to a free electron the kind of electric field that you would be needed. You would need gigavolt per centimeter, and you cannot only achieve kilovolt per centimeter in a lab. So the effect on which we rely is to have, there is an amplification of the electric field inside a molecule. If the molecule has a very heavy nucleus, a molecule with a Z value, very high Z value, like a molecule containing thallium or very heavy atoms, then there is an anti-shielding effect, which means that when you apply kilovolt per centimeter outside, you have internal field of gigavolt per centimeter inside due to the proximity of this highly charged nucleus. And so the experiment consists in having trapped molecules in a high vacuum, apply an electric field in one direction or the other, and look at the difference of spectral line using, again, the Ramsey interferometry, which is very precise. And up to now, and there are competing groups in Harvard, Imperial College, GILA, and up to now, the precision reach is 4 times 30 electron centimeter. At this level, no difference has been seen, and so no electric diamond moment found. Now, if you look at this number, and if you look at the kind of defect of sphericity you're looking for, it is 1 part in 10 to the 17. It means that if you look at the electron as a sphere, it will bulge or be flattened by 1 part in 10 to the 17, which is very, very small. If the electron had the size of the Earth, delta R would be 1 angstrom. So you're talking about 1 angstrom difference on the sphericity of the Earth. But if you found this electron asymmetry at this level, and this is within 1 order of magnitude of what can be achieved now, it will be an evidence of new particles, maybe a connection with dark matter, but it will certainly have an important implication for quantum physics and cosmology. Now, I would like to conclude by one historical example. This kind of question, which is a question about symmetry breaking, is the electron spherical or not? It's a breaking of essential geometrical symmetry. This question was raised 3 centuries ago in the 1730s and 40s. It was a question raised by Maupertuis in 1736 at the French Academy of Sciences. Is the Earth exactly spherical? So this is why I made the comparison with the Earth. So we see the difference. At that time, there was a controversy between theorists and experimentalists. Huygens and Newton had said that the Earth should be flattened because it's rotating. There is a centrifugal force, and so matter should be expelled from the equator, and so the Earth should be flattened. So it was the ellipsoid of Huygens and Newton. On the other hand, an astronomer, one of your ancestors in astronomy, Cassini, which was a dynasty in France. The Cassinis were the royal observer of the French king. They had made measurements of 1 degree of latitude in the south and the north of France. And they said that it is a little bit smaller at the north than in the south, which means that the Earth is elliptical, but in the opposite direction. So it's not like an orange, it's more like a lemon. And there was a lot of discussions. And so the Academy decided that one expedition should be sent to the North Pole with Maupertuis. So you see he has a lot of fur because it was cold. And La Condamine was sent to South America in the Spanish territory of Ecuador and Peru. And they measured 1 degree, the distance of corresponding to 1 degree of latitude difference. It involved a lot of trigonometry, telescopes, measuring length of one basis of a triangle, and a lot of things happened. The two expeditions lasted for more than a decade, and the result was that indeed Newton and Huygens were right. But you see the result is 3 parts in 10 to the 3. So it's 14 order of magnitude less precise than what we are looking now for the electron. But what I want to tell you is that the scientific method has not changed. The precision and the amount of knowledge has tremendously increased. And two things are always the same. Research has always taken a lot of time and a lot of money. But at that time, it was more adventurous than it is now, because some of the people on this expedition did not come back. And the one who came back sometimes were handicapped for life, and because of either physical or psychological outcome of this kind of expedition at the time. This is the memoir which was sent to the French Academy of Sciences, the figure of the Earth determined by the gentlemen of the Royal Academy of Sciences who have measured the degree of the meridian at the polar circle. So this was when Maupertuis came back 2 years later. He had found that the degree of latitude was bigger at the poles than in Paris. So for him, it was enough. He did not need La Condamine. So it gives us also a view about the competition which already existed between scientists at the time. He did not wait for La Condamine to come back to give his conclusion. You see also that these are the gentlemen. There were no women in the French Academy of Sciences. The first woman was elected 3 centuries later, I'm afraid to say, in the 1970s. But I want to point the constant search of new knowledge, which is based on curiosity. You want to answer a fundamental question. It requires testing theory by observation. You cannot just rely on theory. You have to make sure that the theory is right by doing observation. You need to justify why you spend all this money on that. And I will come back to this point. It is still the case today. You need time, trust, and money, which is still the case today. You use the latest optical technologies. In this case, in fact, Maupertuis and La Condamine used sextants which were developed by Bradley. In England, Bradley was the first to measure the aberration of stars, and Bradley was loaning his most precise instrument to these expeditions. And it means also international collaborations. Celsius was with Maupertuis in Lapland. And in fact, the measurement of the temperature was important because the poles which were used the first poles were metallic poles. And in the polar circle, when you put a metallic pole on the ice of a lake, it was just shortening by an amount which was much more important than the effects they wanted to see. So they had to correct for that. And Bradley, I told you already, you need also systematic accuracy evaluation, systematic errors, and so on, and make a lot of corrections. So it's amazing to see all what is written in this paper. And what I want to say is that 3 centuries later, lasers make possible geodetical surveys of the Earth, which of course confirms the fact the Earth is flattened with the pole, but with much higher precision. Now you can measure the small changes of density of the Earth, and you can make geophysical studies, find out what is under the ground, measure small variation of the density of the ground, which would allow us maybe to predict earthquakes. And you have another application, which is a detection of gravitational waves, which is another effect of gravitation. And so I would say a few words about that. But what I wanted to tell you is a point important. You have always, and already at that time, you had to justify the money you spent. And you see here, this is in French, but this is in translation in English. The academic was thus divided. Its own lights had made it uncertain whether the Earth is flattened or elongated. When the king wanted to decide this great question, which was not one of those vain speculations with which the idleness and useless subtlety of philosophers sometimes occupy themselves. This is a sentence for theoretical physicists, but which must have real influences on astronomy and navigation. And so it is, of course, the last sentence which attracts the interest of the king. In the 18th century, it was a century in which the Earth was explored, not only for geophysical reasons, but also for finding new riches, new minerals, new spices, and so on. But I conclude also by just showing you here another application of the laser precision, which is the detection of gravitational waves. So I don't want to insist here on that, but you have here you see the two antennas which are in Washington State and Louisiana, and the first signal was observed by looking at the coincidence of this this burst of gravitational wave observed simultaneously by the two antennas. And the slight shift in the arrival time gave us a first indication of where this happened. And now we have a third and a fourth antenna in Italy and Japan, and we can make trigonometric measurements. And so this is a field which you certainly know about. I just want to stress the fact that it is a real tour de force, because it detects, as I said, less than 10 billionths of an atomic diameter difference between the distance of mirrors separated by 4 kilometers. And just to make on a fun note, you see here the Maupertuis's tomb in Paris. And Maupertuis died in Switzerland, but his body was brought back to Paris, and this is a tombstone. And you see here an angel which is flattening the earth with his hand. I remind you that Maupertuis was the man who discovered the principle of least action, and now Planck constant is an action, and the principle of least action is very important in quantum physics and maybe in astronomy too. So Maupertuis was not only an experimentalist who went to this kind of expedition, but also a theorist. And at that time, this kind of experiments and this kind of observation it was a time of the Enlightenment, and all the salons and the places where learned people were discussing were very much excited by that. And Voltaire was a friend at that time and then became an enemy of Maupertuis, wrote a very nasty poème. These are two verses in French. Vous avez confirmé dans ces lieux pleins d'ennuis ce que Newton connut sans sortir de chez lui. You have confirmed in these boring places, the polar region, what Newton knew without leaving home. And so this means that at least Voltaire did not know a very important point about science. In science, observation or experiments must confirm or infirm theory. So it's not enough to know that Newton had predicted that. You had to make sure that it was right. And just to conclude, I show you here a book that I wrote a few years ago in which I discuss some of these experiments and some of these points about quantum physics and the connection between basic and applied science. It has been translated in Spanish, so you can read it either in French or in English or in Spanish if you want. And I will conclude here and apologize for having been maybe longer than predicted or expected. Thank you.
Okay, so thank you very much, Professor Haroche. We have time to maybe 2 quick questions, if anyone wants to ask anything.
Thank you for your talk. I must start to confess it, and I'm not expert in this field, so my question may be naive. But I'm curious, in your last sentence, you said that confirming that the electron may have a dipole moment which is larger than predicted, may have important consequences in quantum physics and in cosmology, for instance, by some inference with the dark matter. How Can you develop a bit more on that?
You mean-
Why is that? Why is that important that the electron, if
No,
the electron
because-
has a
because-
dipole moment larger than
Because
expected?
if the electron has, if you look at the evolution of the electron in terms of, for example, Feynman diagrams, it means that you have virtual processes in which new particles, supersymmetric particles, are emitted and reabsorbed at a very short time level. And so if you have an electric dipole moment of the order of 10⁻31 or 10⁻32 electron centimeter, it gives you, it allows you to include or to exclude some models, some supersymmetric models. And what I did not say is that at this level of 10⁻30, there are already several models which have been excluded. And so the region of where you can look for new particles becomes smaller and smaller. The point is that these kind of experiments are very refined, but they're not expensive at the standard of high energy physics. An experiment of this kind costs a few $1 million and not a few tens of billions of dollars as an accelerator would. And moreover, they are reaching the point where it becomes, the brute force acceleration becomes impossible to perform. I think the next accelerator will be the biggest one, what I can think of at least in this century. Whether these experiments are still making progresses. If you make 1 order of magnitude improvement in sensitivity every 5 years, it gives you a lot of hope that you will reach a level where this kind of virtual process will be observed. In other ways, we are trying to look indirectly, not detect really this particle, but detect the effect that the virtual creation and annihilation of this particle will have on things that you can observe. But these are becoming, these experiments are of course becoming more and more difficult.
Are you in your group pursuing that type of experiments?
No, my group is working on more on the quantum information aspect, the fact that you can store information in matter state or in photon state and have them interact with each other and so on. But the experiments are also very difficult because then it's a question of scaling up. What you need is to be able to scale what you can do with a few particles, a few tens of particles, to a level where you have millions or billions of atoms all well controlled in position, in state. And this is a formidable challenge. It's called quantum error corrections. And I am not very optimistic about the quantum computer, but I am fascinated by all you can learn about what entanglement is about and about a lot of other things. For example, the atomic clocks, optical clocks, use all this concept of quantum information that I didn't have time to discuss to correct the clocks and to make advantage of all the precision you can get when you have particles located at a well-defined position and interacting with each other. Even if they interact slightly, they still interact with each other. And if you want to make sure that this does not decrease the precision of the system, you have to understand this at with a very high level of precision.
Thank you.
Thank you. I have a question about the QCD cavity. How long is it to read the number of photons that you have in a cavity? Because I think in astronomy, we are really interested to be able to detect photons. So how long is it to do the reading of it?
What we do is that, well, in our case, it's microwave photon cavity, and we use the light shift effect to detect them. And of course, if you have only 0 or 1 photon, a single atom will end up in one state or the other, so you can detect this easily. If you have more than 1 photon in the cavity, you need to use more certain method to change the light shift so that each atom will give you one bit of information. For example, if you have up to 7 photons, you need 3 bits because 2 to the 3 is equal to 8. If you have 15 photons, you will need 4 bits. So the number of atoms which interrogate the system increases, and we have been able to count photons up to 6 or 7 in this way, but you could expand it to more photons if you change your system, and in this way, you get interesting information. Another thing I did not have time to talk about is the fact that you can use this to prepare field state in a superposition to build what we call Schrödinger cat state of a field which are at the same time 0 photon and 8 photon, a superposition of the two. And this kind of state contains a lot of information which could be used in processes to build a computer or to make quantum simulation. So it is useful for up to now, it has been useful for quantum measurement because you get a lot of information in the phase of the system, which give you a high precision if you want to measure a very small electric or magnetic field, things like that. So it's more realistic now to talk about quantum measurements than to talk about a quantum computer. The quantum computer will be a Schrödinger cat with billions of particles in it. And this will be closer to a real Schrödinger cat, which is a dream. You cannot think of a system containing a macroscopic number of particles maintaining a superposition of two different states because of decoherence. So the study of decoherence and the way to find decoherence is an important part of this process. What I want to say about the connection with your field, it's I think more in the technology. The fact that the instruments that we use are closely related. For example, to build these arrays, optical lattices, we start by focusing a plane wave, which gives one spot. But if you want to have a lot of spots, what you can is to modulate the plane wave before the lens, and you get the Fourier transform of the modulation, and it's exactly the kind of techniques that we use for adaptive optics. So in fact, our system, which builds these lattices, are adaptive optics using light modulators, same kind of light modulators which are used in astronomy to correct the plane waves.
Okay, unfortunately, we have no time for more questions, but we have a coffee break now in the cafeteria where you can continue asking Professor Haroche any question you want. So we thank again for your talk. And just a reminder that tomorrow at the same time, we have another colloquium by another Nobel Prize of Physics. And please, the students come down so we can note your attendance. Thank you. And now